Hello everyone, and welcome back to the Solutions Unit. In part 4 of these videos, I'm going to be talking about KSP and what it is and what it does. Let's get started. So KSP stands for the Solubility Product Constant. That's where the S and the P come from. And so essentially what we're doing is talking about the solubility of something, and typically we're talking about the solubility of something that is considered to be insoluble. So, solubility of a solid can be defined in terms of the number of moles of the solid that will dissolve in a liter of the solution. So moles per liter, you should recognize that as molarity. It's a measure of the degree of dissociation of the ionic solid in solution, specifically for compounds that are considered insoluble. So for example, let's just say calcium sulfate is supposed to be insoluble. That means it's not supposed to dissolve at all. But what do we mean by at all? What if maybe one molecule out of a mole will turn into a calcium ion and a sulfate ion? If only one molecule out of an entire mole will dissolve, would you even tell that it's dissolved? And would you consider that soluble? What if 10 molecules dissolved out of a mole, or 10% of the molecules in a mole dissolve? Would that be considered soluble? Well, KSP is going to kind of answer that question for us. The solubility of typically insoluble things. So here are some example values of KSP. Notice that they're typically all very small numbers, like something times 10 to the negative 7 or something times 10 to the negative 15. Also, what you should know is the smaller the number gets, the least soluble or the less soluble the thing is. So mercury carbonate is less soluble than nickel carbonate. Nickel carbonate is more soluble because the KSP value is a larger number. So let's get started trying to write some KSP expressions. And these are not in your notes, but we're just going to practice just for a minute trying to write KSP expressions. So we'll start with something that's typically an insoluble solid, AgCN for example. And that insoluble ionic solid will, if it dissolves, dissolve into its ions. So that's silver cyanide turning into silver plus and cyanide minus. So the KSP value is just like any other equilibrium constant. It's products divided by reactants raised to the power of their coefficients. And there are no coefficients here, so just products divided by reactants in this case. And then something like this. Again, this is not in your notes. You do not have to write it down. This is just to get a visual and an idea before we move on to the problems that actually are there. Okay, but now we need to figure out what exactly this means. We're talking about AgCN solid. If it dissolves at all, it'll dissolve into an aqueous Ag plus ion and an aqueous Cn minus ion. So hopefully you're noticing something here that's off, which is the AgCN solid. Solids are not included in the KSP expression, just like they're not included in any equilibrium constant expression. So the equilibrium constant expression is only the Ag plus and the Cn minus, and that's it, not the AgCN. Okay, let me show you another one. I've got BaSO4. So if this insoluble thing were to dissolve, it would dissolve into Ba plus 2 and SO4 minus 2. So again, this insoluble thing is a solid. If it were to dissolve, it would dissolve into these two aqueous ions. So the KSP expression becomes Ba plus 2 times SO4 minus 2. And that's it. That's all you got. That is your KSP expression for BaSO4. Now take note that this plus 2 and minus 2, these guys are not like squared or cubed or anything. That's just a plus 2 and a minus 2 because of the charges. So if we looked at one more, let's say PbBr2, solid. If it were to dissolve, that'd be into lead and bromine. Now I want to take a minute to talk about where the 2 comes from and where the 2 goes and why the 2's here and there and the other. So first I'm going to look at the 4 on BASO4. Now why is there a 4 here, and why is there a 4 there? What's the 4 coming from? Well, that's coming from the identity of sulfate. Hopefully by now you totally remember and recognize that sulfate is SO4 minus 2. The identity of sulfate is that there are 4 oxygens. That 4 doesn't have anything to do with the balancing the charges, because barium's already a +2 and sulfate is already a -2, and so those are going to cancel by themselves. But when we look at PbBr2, what is that 2 there for? Well, I know that bromine is a -1, and since there's 2 of them, lead has to be a +2. So the reason that that 2 is there is to balance charges. It's not because of the identity of bromine, it is there to balance charges. So if it's there to balance charges only, then it disappears, or it is no longer a subscript. It does not come down at the bottom of the Br2 at the end. This is not diatomic bromine. This is ionic bromine, or aqueous bromine dissolved in a solution, not the bromine off the periodic table of the plain molecule. It's the same thing as sodium chloride NaCl turns into Na plus and Cl minus. So PbBr2 turns into Pb plus and Br minus. 2 of them, because this number here is used to balance charges, not because of the identity of bromine. So remembering that will help you write the equations. And since we know that, then the KSP expression actually becomes relatively simple. It's Pb plus 2 times Br minus squared, because that 2 is now a coefficient, and so it will become an exponent. So I have one more that I'm going to show you, and let's see if we can get it. So this one is Cu3PO4, typically considered insoluble, but if it were to dissolve even just a little bit, it would turn into copper ions and phosphate ions. So let's look at which of those subscripts move to the other side and which of the subscripts don't. Phosphate I know is a -3 charge, and since there's 2 of them, that probably tells me that copper is a +2 charge. So over on the right-hand side, that copper is a +2 and the phosphate's a -3. The 4 here at the bottom is the identity of phosphate. So that 4 automatically carried over to the other side, but the 3 and the 2 were there to balance charges only. And since they're there to balance charges only, they disappeared on the other side. Now, in order to get the entire reaction balanced, everything to balance out the way it should, since there are 3 coppers on the left, I still want 3 coppers on the right. And since there's 2 phosphates on the left, I still want 2 phosphates on the right, and that's going to make everything balance for me. If you want to check it out, if you don't believe me, I'm going to go ahead and erase all that so that it gets out of the way. On the left-hand side, I have 3 coppers, and on the right-hand side, I have 3 coppers. On the left-hand side, I have 2 phosphoruses and 8 oxygens. On the right-hand side, I have 2 phosphoruses and 8 oxygens. And over here on the left, I've got a neutral Cu3PO42. And on the right, I have 3 Cu plus 2s, which is a total of +6, 2 PO4 minus 3s, which is a total of -6, which makes the right neutral as well. Now, all that really doesn't have anything to do with KSP. That's just to remind you about how to write a balanced equation. So the KSP itself is just the products Cu plus 2 raised to the power of its coefficient, so cubed, and PO4 minus 3 raised to the power of its coefficient, squared, and then leaving out the Cu3PO42 because it's a solid. So all of that was just to give you an idea of writing expressions and writing equations, and now let's get into the actual math problems that are in your notes. Okay, so the first problem we've got is the solubility of CuBr is 2 times 10 to the -4 molar, which means 2 times 10 to the -4 moles of CuBr will dissolve in a liter. calculate the value of KSP for CuBr at 25 degrees, and notice that they're giving us the KSP expression, which is the products Cu plus and Br minus, and not divided by the reactants because the reactant CuBr is a solid. So the KSP expression is already given. Let's just try to plug in. So the solubility, 2 times 10 to the negative 4 moles per liter, means that if we had 2 times 10 to the negative 4 moles of CuBr in, let's say, a liter of solution, that many moles would break up into Cu plus and Br minus. Since it's a 1-to-1 ratio, that means that we would have 2 times 10 to the negative 4 moles in a liter of copper plus and 2 times 10 to the negative 4 moles in a liter of Br minus, because all of that CuBr, 2 times 10 to the negative 4 moles per liter, will break up into Cu plus and Br minus. So using the KSP expression that's so nicely given to us, we have two times 10 to the negative 4, essentially squared. And 2 times 10 to the negative 4, 2 squared is 4 times 10 to the negative 8. KSP, just like regular K and KC and KP, does not have a unit. It is dimensionless. So KSP is 4 times 10 to the negative 8, and that's it. Let's move on. So the next question says the solubility of CaF2 is 2.15 times 10 to the negative 4 molar, which means 2.15 times 10 to the negative 4 moles of CaF2 will dissolve in a liter. Since it's a 1-to-1 ratio, CaF2 to Ca plus 2, that means that there's going to be 2 times 10 to the negative 4 moles of Ca plus 2 in a liter. But notice that there's a 2 here in front of the F, which means that for every one CaF2 that are dissolved, you'll get 2 F minuses. So you'll have twice as many F minuses as you have molecules of CaF2, which means that you're going to have 4.3 times 10 to the negative 4 moles of F minus for every liter of solution, 2.15 times 2. And I just see that I left off the 0.15 in the Ca plus 2, so make sure we add in that 0.15 in there. So now with my KSP expression, I can just plug in the numbers. Ca plus 2 times F minus squared, so that's going to be 2.15 times 10 to the negative 4 times 4.3 times 10 to the negative 4 squared. So we'll take that 4.3 times 10 to the negative 4 squared, multiply it by 2.15 times 10 to the negative 4, and I end up with 3.98 times 10 to the negative 11. And that is my KSP value for CaF2. Alright, here's my last question for this video. Calculate the solubility of CuIO32 at 25 degrees, and the KSP this time is given. So essentially we're going backwards. Using the KSP, find the solubility. Let's start with the balanced equation. CuIO32 makes a Cu plus 2 2IO3 minus. Remember, you've got to know why the 3 is there. It's from the identity of iodate, but the 2 is because of balancing charges. So the 2 becomes a coefficient while the 3 stays as a subscript. So if I write the KSP expression, hopefully it should look something like this. Cu plus 2 times IO3 minus squared. So now, since we're looking for the solubility of CuIO32, let's think about how that CuIO32 would break if it were to break up. Well, there's a 1-to-1 ratio between copper iodate and copper. So for every 1 copper iodate, or for every X copper iodates, there'd be X number of coppers. But since there's a 2 there for the iodate, for every X number of copper iodates, there'd be 2X number of iodates, twice as many iodates as there are copper iodates. So when I'm trying to plug numbers into my KSP expression, that KSP expression, 1.4 times 10 to the negative 7, I don't know what I wrote 4, let's make that a 7, that's going to be x times 2x squared, x times 2x squared. So 2x quantity squared is the same thing as 4x squared. times x, which is the same thing as 4x cubed. So we have 1.4 times 10 to the negative 7 equals 4x cubed. Let's first divide both sides by 4 so that the 4's cancel out, and we end up having 3.5 times 10 to the negative 8 equals x cubed. Next step is the cube root of both sides. If I take the cube root of x cubed, that becomes x. And the cube root of 3.5 times 10 to the negative 8 is 3.27 times 10 to the negative 3. Please stop here, pause the video here, check to make sure you can get that number on your calculator. Figuring out how to use a cube root on your calculator is pretty important, and you need to be able to do it. So pause, make sure you're getting the same answer as I am, and then start the video again. Okay, so now that is x. This value of x can fit in there to the expression. It can fit in here, and more importantly, it can fit in where the CuiO3 is. So that x is actually the number of moles per liter of CuiO3 that will dissolve. So my final answer is 3.27 times 10 to the negative 3. So let's look at the second part of this problem. How many grams will dissolve in 2 liters of water at 25 degrees? So we had already decided 3.27 times 10 to the negative 3 moles will dissolve in a liter. Now this is asking how many grams will dissolve in 2 liters. So let's multiply that by 2 liters instead of just 1, and I end up with 0.00654 moles in 2 liters. But I don't really want moles in 2 liters, I want grams in 2 liters. So I'm going to factor label moles to grams. This is, again, CuiO3 63.5 for a copper, 126.9 for an iodine, 16 for an oxygen, 2 iodines, 6 oxygens, and that's a grand total of 413.3. So that's 413.3 there for my math, and this ends up equaling 2.70 grams. That's how many grams will dissolve in 2 liters. Alright, I hope you join me again next time for QSP and KSP and the common ion effect. See you then.